I'm happy to notice that the course is also becoming like a social event. It seemed like I could just, give you some time to discuss and just enjoy the company of each other, and I think that's a good sign. It would also be useful in the future because let me give you a quick outline of where we're standing. So we're like in really the middle of the course. You had 3 lectures given by me and another lecture given by Ron. We actually have only another 4 lectures coming up, and then we move the baton to you to be presenting the finals, okay, which will take also something like 4 weeks or so. So how is that going to work? Let me give you a bit more details. So each one of you is supposed to come up with a suggestion for a question that is of interest. It could be biological, it could be sustainable, it could be anything else actually. It could go pretty far. We've seen in previous years a lot of academic freedom in framing the questions. And then the idea is to try and give more insight into the answer to that question based on using numbers, back of the envelope estimates, pulling together numbers from the literature, anything in the spirit of the course that again could be interpreted quite broadly. You're also welcome to bring gadgets with you to have, to make a poll to engage the people in the audience. Everything is allowed. Okay? And it's going to be 5 minutes on the whiteboard, which I know is intimidating and challenging, but at the same time, it's also something that's actually, and I heard it from, several people along the years, it's also like kind of like a skill or something that once you do it, you're in much better position for the rest of your life when you need to face anything vaguely similar in terms of challenge. In order for this to work, to be successful, you also have to practice. And we're trying to build some sort of a structural way in order for you to build up. It's not like I give you now this and like you go and do it. There's a process of mentoring, not unlike what we see in reality shows of, I don't know, X Factor or whatever. The idea is that like we'll have, once you have, an idea, the idea is that the next step is to find a mentor, meaning somebody in the group that you'll pair together with, and then you'll be getting feedback as you work along on it, on how does it feel, look, understandable, etc. Usually it takes more than one try until you have it more smoothly. It's also good to practice on, say, if you're in a lab with your lab members, if you're not in a lab with your family members, with your friends from anything, and like with that try to smoothen it in the sense that like it's quite amazing how much does it take in order for things to be such that they reach a diverse audience. It takes time, so it's another thing to practice on. All of that has some timeline, and all of this is summarized not by me talking, which is easy to forget, by like a one-pager of how the finals work, and we'll be putting it on the website sometime today. Hopefully also already with the dates that you were assigned when to give it. If there's a problem, let us know. Okay? Now the silence. Everybody were bustling with activity, now the silence. Any thoughts, questions, comments on this? I know in this work you need to work hard. It's both the exercise that you need to do, on which we see that you're doing serious work, and there's only another 2 of them, right? So no despair, just another 2. And the major next thing for you, no test, no need to memorize things, anything of the sort. It's just this final. Okay? And the final is, again, what you'll do on the whiteboard in your 5 minutes of glory. But there's also another side to it. You also need to hand in like a 2-3 page vignette, kind of like what you're reading in the exercises from the book, that again writes the question and does some calculation, gives also there's a bit more space to put some, historical background or something. Why is it important or why is it cool? Do the calculation, add anything you want, and then some, punchline or whatever is in the end. Okay, and that together, so what you'll be presenting in front of the class and what you'll be doing in this short few page summary would be half of your score, half of your final grade, and half of the final grade is based on the exercise and you participating in class. Okay? Good. I would say that the common thing is to first, to prepare, because there's a timeline, everybody prepare to the deadline of doing the presentation. And then they say, and afterward they do it, we also need to write these 2 pages. I think some of the best cases were when people were starting to write this even before or while preparing for doing the thing on the whiteboard, because it's actually very synergistic. Like the fact that you write things makes it more clear in your mind, and then you just, after you do it in front of the class, you can improve it some more. As you'll see, the way we're doing it is there's about, 13, 14 people in each 2 hours doing those 5 minutes of glory. So you'll see you'll have to be ready to do it on time. Unfortunately, we can't have you, going a lot over time. And you'll also see that we're giving feedback. So when you'll be sitting in those sessions, the people on the audience would also send feedback to the people doing the presentation, constructive feedback that would also help improve the final write-ups and things like that. So there's a lot going to happen. If you want, you can invite people to join. If you have friends who are interested into something like that, to the finals, it's actually kind of engaging and very diverse and stuff like that. Okay. Yeah.
Do we need an approval for the idea?
Yeah.
Okay.
Good point. Yeah. So we'll be sending you the dates and everything, and you'll send us what you decided to work, what you want to present, and also who's your mentor, and there's a whole protocol to the whole thing. Good. So all of this thing is probably pretty vague still. So it's good to have an example. We might also be able to send you some examples of previous years, but happily we had a courageous student who was willing to give an example already now. So Sam, the floor is yours.
Thank you. Hi, everyone. So in the last 18 years, over the entire world, we have searched more about spinach than we have about climate change, which is pretty crazy to think about. Now, why am I telling you about this? Well, the large-scale attention received by the World Cup motivated us to think about how does the attention received by the World Cup compare to other topics such as climate change and more recently and more specifically the climate conference COP27 that happened last month. And we term this work COP versus cup. Okay, so our question is, what is the ratio of attention given to the cup versus the COP or climate change more generally? And just as a few options, I would like your thoughts before we go ahead. Is it about 10 to 1 in favor of the World Cup to COP? 100 to 1? 1,000 to 1? 10,000 to 1? Or 100,000 to 1? Okay, so raise of hands for who thinks it's 10 to 1.
What are you measuring?
So we're measuring the ratio of the attention given to the World Cup versus the COP conference that happened last month, or generally. Okay.
Attention is Google Trends.
Google Trends, social media statistics, we'll talk about it in a bit. Let's not think too much about this. It's just I want initial thoughts. Okay, so 10 to 1, raise of hand. Okay, 100 to 1. Okay, a few. 1,000 to 1. Okay, about half, maybe a bit more. 10,000 to 1. Okay, about the other half, and then 100,000 to 1. Okay, just a few. Okay, so what do I mean by the World Cup is large scale? Well, why don't we try put a number on it and come up with something ourselves? Okay, and what I was thinking is the amount of time we viewed the World Cup. And I'm using 2018 numbers, but it's similar this time as well. Time viewed World Cup. Okay, so I want us all to come up with this together, because I think most of us are watching the World Cup. By the way, show of hands, who watched the game last night? Okay, and how many of you would say that you're engaged or passionate about the climate crisis? Okay, good. So let's try to come up with the time view. Okay, and the way we're going to do it is we're going to do views per game, and then live views, non-live views, all of them. Then we're going to look at minutes per view, and we're going to do number of games. Okay, so I want all of your help here. How many views per game do people think it is? Any thoughts? 100 million? 10 million? What else do we get?
Including the people in the stadium?
Including that, they'll be negligible, but yeah, okay. So I think about 100 million we got. So 100 million. Okay. How many minutes per view do we think it is? What are people's thoughts? 60, 90, 100, something like this. Okay, so 70. Okay, so let's put it at about 100 minutes per view. And by the way, these numbers are roughly what the official statistics are. I checked them. Okay, and then the number of games. Okay, so we have 8 rounds in the World Cup. So it's 2 to the 8 for the number of games, which is 64 games, and let's just say 100 games in total. Okay? Good. So now let's calculate the total.
2 to the 8 is 256. 2 to the 8.
Ah, did I get that completely wrong? No, sorry, it's 2 to the 6 round.
2 to the 6.
2 to the 6, sorry. Yes, thank you. Thank you. Okay, so the total number of minutes watched is, okay, so we have views per game, so 100 million views per game multiplied by 100 minutes per view and multiply that by 100 games. Okay, so this comes out to 10 to the 8 multiplied by 10 to the 2, 10 to the 2, which is 10 to the 12, and what are the units? So we can cancel views, games, and we have minutes. So 10 to the 12 minutes watched. Okay, so that's 1 trillion minutes, which is a pretty stupidly large number. What does this actually mean? Okay, so let's think about this in terms of how many human lives that is. So how many minutes in a human life? Min's life. Okay, so we have about, let's say, 100 mins per hour. We have multiplied by 10 hours per day, 100 days in a year, days per year, and 100 years in a life. Okay, I'm running out of space a bit, but I hope you can all follow that. Okay, so this is 10 to the 2 times 10 times 10 to the 2 times 10 to the 2, which is 10 to the 7, and then units is hours cancel, days cancel, years cancel, so it's minutes per life. Okay, so 10 to the 7 minutes per life, and we have 10 to the 12 minutes here. So let's just see how many lives we have. It's 10 to the 12 mins divided by 10 to the 7 mins per life, and we end up with about 100,000 lives equivalent. Okay, so 100,000 people have to watch the World Cup. And how many is 100,000? Let's think about it in terms of football stadiums. It seems pretty relevant. How many people fit in a football stadium? Can I have some numbers?
80,000. Let's say 100. 100,000.
Okay, so a few tens of thousands, something along those lines, 100,000, something like that. So let's go with few tens of thousands of people per stadium. Okay, so the number of stadiums needed is number of this is people per stadium. Sorry, people in stadium. So the number of stadiums is 10 to the 5 people divided by few 10 to the 4 people per stadium, and we end up with we need a few stadiums worth of people to watch all of the content that we've viewed, and these people have to sit in that stadium for their entire lives to consume the amount of media that we did for the World Cup. Okay, so this is a pretty mind-boggling number. Now let's think about how much attention did climate change receive in comparison to the World Cup. So what we did was we looked across different social media platforms, Twitter, TikTok, Instagram, that kind of stuff, and we also looked on Google Trends to see how many Google searches there were. Now, for the social media platforms, what we found was something along the lines of, so when we looked across official accounts of COP, the UN climate crisis, and FIFA and the World Cup, we see a difference of about 100 to 1,000 fold more attention received by the World Cup than climate change of COP. So it's somewhere around there. And for Google Trends, what we see is we see that when we look at the peak attention given to COP27, which was last month, and compare that to the peak attention received by the World Cup, which is around now, the number of searches for the World Cup is a few thousand times more than COP was on Google Trends. Okay, so the World Cup is receiving vast amounts more attention than climate crisis, and what do we hope to get from these is we want people to think about how much attention we give to different things and how much we really need to be thinking about the climate change more and how we can learn from the attention received by the World Cup to give more attention to climate change. And I just want to end on when we look at how many searches there are for Taylor Swift since 2004 and compare it to the number of searches there are for climate change. Taylor Swift has 2 times more searches than climate change. In her words, haters gonna hate. Thank you.
Okay, so I think you had a good impression. Thank you, Sam, for being willing to take it upon yourself. Yeah, so you can bring all your passions, creativity, whatever you want into the kind of final project you'll be doing. Yeah, and okay, let's move from here. I would say that this is I think it was done in a very energetic mood, and there's something I think many of us smiled along throughout the presentation. I think it's also meant to be I think to cause us to pause for a minute and to think about our decisions, where are we heading, what's happening. There's also this side to the things, of course. Good. So last time you were talking a lot about the human body and the cells that constitute it. And today the lecture is all about rates. And so in the spirit of going from the previous lecture to this lecture, let's talk about the turnover in the body. Let's make it a concrete question. How long does it take the body to, how to call it, to create cell, no, not good. Just 1 second. I need to rethink how to frame the question well. Okay, so the question is this. Let's see if I can, then I can write it. In writing, sometimes it's more difficult than talking. We're thinking about the cells in the human body, and they turn over. And let's say if I took the average, or if I was looking in total, what's the mass of cells that are being turned over in the body, how long would it take until the body creates a cell mass equal to the whole body weight? Okay, now the question is clear. How long until created
to replace its body?
Cell. What?
How long does it take the body to replace its body weight?
It's not really replaced, right? We
not
are
all cells.
just like producing.
Some
Okay.
cells.
We're producing.
Equivalent to the weight.
Okay, so let me clarify that in a second. But this question actually I didn't come up with it myself. It came up originally in the mind of some Greek philosopher or whatever, and it turned out into this classic question about the shipothesis, which is about this question actually of identity, of if you have a ship and now after a while you replace the sail that got ruptured, and then afterwards you replace the oars, and then you replace, and in the end you replace all the different components. Is it still the same ship or not? Okay, it's kind of a deep question. It's not something we vote about. It's somewhat deeper. But we can take the version that just talks about the quantitative aspects of it and ask, okay, how long, if we're the ship of Theseus, how long does it take to replace us? Okay, and if you try Googling it, there's a claim that this happens once every 7 years. And now I guess my question to you is it A, shorter, B, about right, or C, longer?
If we're just looking at the mass,
Yeah, if you're just looking at cellular mass.
shorter.
Okay? Question is kind of clear? Okay. Who's voting for shorter? Half of the people. Who's voting for about right? Who's voting for longer? Okay. So now the question is, how do we approach this in in a rigorous manner to try and get an answer? Okay. And actually, we're interested in more than just this specific question, but just to learn things about the turnover of cells in the body. Now, clearly, the original statement of the ship of Theseus is thinking about like the whole body replaces itself. That's the question of identity, right? But that's kind of like if you know a bit more about physiology, you know that's not the case because there are cells in our body that don't replace themselves. Kind of like what?
Neurons.
Like neurons. Although there are claims, when you start looking deeply, there might be some changes there, but clearly not, so rapidly. Anything else?
Muscles.
Muscles. I think muscles are really replaced.
Yeah, but
Very low?
Very slow.
Okay, very slow. Okay, I think also in the cornea, in the eye, I think it also doesn't replace itself. What? In the heart, yeah, so there's actually a lot of research about the heart. It turns out it was thought that it doesn't replace itself at all. Now they find like cool methods that it does replace, but kind of slowly. Okay, so clearly we want to say it's not exactly the original question, but we're talking about this kind of framing of how fast does that work. Okay, how do we go about trying to deal with this question? So the reason also I'm giving this is also not because it's just an interesting question. I think there's also a more general point here. And that's the kind of problems where on the one hand, you have a pool of stuff that is created with some rate. And where we're interested, as a result of that, what happens in terms of the turnover. And there's a relationship where the pool size is equal to the rate times the turnover time. Okay. It's not unlike, we know like about, distance equal to velocity time duration. So it's kind of similar. Okay, let's move into a concrete example. You were talking last time about red blood cells, right? Let's see what can we derive from that. So how can we get at the mass? So I want to look at I'm interested in the rate. Okay, I want to know about the production of cells in our body. And we'll start with the production of red blood cells. Okay, as one important type of cells. Okay, so what do I need to know? I need to know the pool size. If I know the rate, somebody knows how many grams of cells, of red blood cells you produce every day?
200 billion.
So I'll be shocked if anybody knows that, by the way. That's very
200 billion.
No, I'm talking about grams of cells per day.
Isn't it
I think the weight of the blood is supposed to be some percentage. It's supposed to be a few kilograms per person, and red blood cells are supposed to be half of it.
Okay, so great. So there's a way to derive it, and that's a way to go in that direction. Okay, but it's the sort of thing that usually the answer of what's the rate of red blood cells production per person. Very, very few people know that. But the question but deriving it might not be that tough. So let's say I want to know the pool size. So the pool size, I'll go according to what you said. So you're saying, so maybe you repeat that again.
I think the blood in adult body should be a few liters. I think about 5 liters per adult, maybe.
Blood about, just a second, 5 liters.
And
Okay, which is about 5 kilograms.
And I think the red blood cells is supposed to be about half of it.
Yeah, so percent, which is red blood cells, it's about 50%. Okay, so from this we're getting P is roughly 2 to 3 kilograms. Okay, good. So we have this. Now we need to get a T, the turnover time. Anybody carries any info that could help us with that for red blood cells? Yeah, so there's this number of 120 days that some of you might remember. It's actually interesting to know how accurate it is, because like 100 is like somehow 100 is like a round number that's easy to remember, but that's really about right. So you could take 100, 120, that's all fine. Okay, so now I have P and I have T. And now I'm interested in R equal P divided by T. So that's about, let's make it 2.5 kilogram and divide it by 120 days. So let's make it 2,500 grams. And we're getting about 20 grams per day. Which, by the way, it's interesting, right? 20 grams. I don't have 20 grams with me, but you can imagine something like you can hold in your hand, but it would be something. It's like, anyway, 20 grams. Okay, every day.
That's the major component of dry waste is red blood cells a lot of the time. Like
In human excrements or whatever it's
Yeah.
called. Okay. So that's great. I have this, and I think you saw the way of trying to approach that. And now, if we want to go, this was just red blood cells. Now we're interested in saying the cellular turnover in the whole body in a day. How do we do that? We have to work hard. Okay, it's not that everything in life, or that I'm claiming in this course that everything could be like I could just do it in 2 minutes on the whiteboard. Some things they require collecting a lot of information. You need to try and analyze. Okay, what are the cells in the body? We knew 120 days, but what is it for the liver? What is it for the muscle? What is it for this? What is it for that? You have to go through some work. Short version is you spend time on it. You come out after a while with two things. One is a value, and one is a paper in Nature Medicine that you can read by Ron Sender. And it comes out to about 100 grams per day. Okay, so there's a point here, right? There's things that you can do quickly, just back of the envelope. Some other things are more complicated. The human body, with all the heterogeneity of tissues and this, it's more complicated. I'm not claiming it everything. And it's good to know, to differentiate, okay, what problems I can do this way, what I can't. Good, just 1 second, yeah.
Maybe you can go from the other side, you can look on the intake of nutrients by humans, then you can kind of going from the other side of not asking how much the body use, it's how much the body takes, and then you can infer it from the
Okay, so there's a cool suggestion.
Efficiency, which is very different between other people, right?
And to neglect everything that is not self-division.
Okay, so there's a cool suggestion here to try and approach it from a completely different angle through the food intake. Then there's a comment here about, okay, whether there's the efficiency in that change, whether it's, what happens across people. I think it's a really cool way, and you can try and do that. It's hard to get at a very rigorous answer, because much of that would go into replacing components within cells. Okay, there's also a turnover of proteins or other stuff inside the cell. That's not what we're talking about. Yeah. Now we talk about the breakdown and reformation of cells. Yeah. So it's kind of different. But I have a million things I want to tell you today. So let me move on. Okay? Good. Okay, so we did this 100 days. So let's just wrap up what we have here. So how long does it take? So the P for the human would be how much? Let's say 70 kilograms. The R, we now know it's about 0.1 kilogram per day. Therefore, T is roughly 700 days or 2 years. Okay, so indeed, like many of you guessed, it's shorter than 7 years on average. Mostly coming from the heterogeneity also in our cells. There are some cells that are, rapidly changing, and some cells in much of our, say muscle cells, as you mentioned, and other things, are actually very stable. And this gives you like some characteristic average value. Yeah.
How different are in different extreme of age? So very, very old or very, very young babies? Because I guess this shouldn't be the same, especially for babies, but even maybe for adults.
Are you the second reviewer from the paper? so there's a lot to be said about it. If you talk with Ron, we could give you the full picture. Great. So how are we doing? We talked about this. We did that. Okay. Let's give you a challenge to deal with. So if I want to apply this, let's say I'm asking you, I'm asking you, how many babies are born each year in the world? Okay, let's take, like 3 minutes, and either by yourself or with somebody sitting next to you, try to come up with an answer. Okay, and I want a number. תבדקו אם אפשר כבר, כאילו, זו שאלה נורא קלה, אבל אמרתי שאני אפשר לחתוך אותם או שהם עובדים על זה באמת? מה? כן, לא נראה שהם... אני חושב מתי נעשה את הריסס. שאתם נראו שה-climate change, transcription translation, diffusion, axon, אין לי איזה מקום טבעי להפסקה. לא, אני יכול, אבל אני פשוט לא מוציא אותם לעבודה. או אין לי איזה אתגר, לשלוח להם איזה אתגר. גם בסדר. Okay. I need you back. So, I think you got the hang of it, right? Like if we want to do that, we need to think in the same spirit. What's the pool size?
8 million. 8 billion.
8 billion people. What's the time? What the turnover time?
1 year. 1 year. Well, we're looking at
Yeah, so like probably something like 70 years. I'm actually curious to see what's the average lifespan now on Earth.
80 something.
Yeah, so I think 80 something is like really very highly developed countries, but I think it's not. But actually, it went up like really amazingly well in the in the past few decades. Like it's very, very impressive what humanity was able to achieve in that sense. Okay, now the rate is P divided by T. So that's 8, 10 to the 9 divided by 70 people per year. So that's about 10 to the 8 people per year. Okay, so we have about 100 million babies per year. Okay. Is there some problem with the calculation?
Yes.
Why?
The dying people, no?
Why? Just 1 second.
Not only growing, like you assume that like the pool is all the world. Like for me, the pool of like birth-related people are like only people that are in age that can give birth. I guess I don't know.
Okay.
I think on the other hand, we have people who are dying.
You need a couple.
The pool
Okay,
is growing.
so there's a few comments here, but one thing I've heard several times is about this thing that the pool is growing. Okay, so this whole thing of doing this calculation, like this thing is accurate, completely accurate, when you're in what's known as steady state. Okay, it's this term talking about the fact that things are in steady state, meaning kind of like stable, the pool size stays the same, and then the flux in and the flux out is the same, and then you can do all the thing with the turnover, everything is fine. Here, the population of the Earth is still increasing. So I'm not strictly in the situation where this, say, equation or whatever holds.
So what rate are we talking about?
Okay. Yet, what's the correct answer?
100.
So I Googled it just on the train when I was coming here. It's 140 million. Okay? Okay, what do I want to say? Many cases, there is this thing about, the strict conditions for doing something, but actually we're not that far in a way. If you want, it's a question of what accuracy you want to get. If you want to get it to the third digit, then you can't do what I just did. But if you just want to get a rough value, even though you're somewhat out of steady state, you can still do that. Okay, there's a pressing, yeah.
Why would you consider all the people and not just women, assuming women are the ones giving birth?
Okay, so that's, anybody has a good, so it's,
You still need a man to do it.
Absolutely.
You need to.
But the rate of babies being born should be calculated, what is the number of babies?
yeah. Okay, so I'll say I'm not sure I
No
have,
matter how they're born.
I'm not sure I have a very good, something that intuitively would, I can understand where the question comes from. And it relates also to the question that Hadass was giving about, whether we should take the relevant time, ages, etc. Okay, this talks about, say, when you do this kind of analysis, you talk about the overall pool. This is why I'm taking all of humanity. And you're looking at the average turnover time, and then you're getting an average rate, and it's valid. That's good. You could start and do could break it down into compartments, say males and females, or people at fertility age, before and after. And then it becomes more complicated, and you'll get definitely double per person, but then it would be half the pool size. So in the end you'll get the same result, but in a more broken down, elaborate fashion. Anyway, I don't know if it's a great way to explain it, but I see where it came from, and it doesn't change the result.
If you consider only women, you have 140 years per individual being alive.
No.
Something along the. I'm not sure that's a great way to understand it better, but it's another way to think about it. Okay, I see there's a lot of
But it just doesn't matter where they come from, right?
Right.
It matters for humanity, but it doesn't matter for the context of this question because they could be sent in from space. As long, what we're looking at is that the pool overall more or less stays the same. That overall, this 70 years is maintained and stays the same. Whether they're sent from space and then sent back to space, or whether they are born by women, or born by men, or born by all, it doesn't matter for the context of keeping the pool the same.
Yeah.
Right?
So it's a good way to say that in a way this sort of ways to think about problems, they really get rid of all the details. Just like pointed out, doesn't matter who's which gender involved in what. We're just taking this black box of saying, okay, we have a pool size, there's a rate, there's a turnover time. I don't care about the exact details within it, and I think that's one of the strengths of this approach. And again, it doesn't answer all the questions. It gives you some answer. It might be that it's super important to get more into details of some other stuff. Okay. Yeah, I didn't know it would create such interest. Yeah.
Is that a good estimation for every population that is not like necessarily in a steady state? Because if the change in the population has like 10 times fold, 10-fold, so it may be like we're gonna be out of that.
Yeah, you are right. So if we do the same type, so here we say we got about a 40% error. Okay. If we did for the state of Israel, which is further from steady state, which is in faster growth, the error would be more, something like around a factor of 2, because of the imbalance between births and deaths. And then you might bring up like a different problem, I know, like COVID-19, when the viruses are expanding, or like, and then you might, so it's a question of, how good would this be as an approximation. So I wouldn't do it on something that's extremely dynamic. But I just wanted to show you that also you shouldn't be too cautious and too conservative, saying, we're not in perfect steady state, I can't do this. No, you can. Just be aware that like the result would be accurate to within some level. Okay. Great. Let's try to now, so implement it on the human body, we implement it on the births. Let's take a completely, another type of question. So moving from a focus on ourself, humanity, to a focus on the place we live in. How fast is climate change moving? What do I mean? So I'm interested to take this, serious problem of climate change and try to give us a more intuitive, like we all know, there's something big happening, and you might hear something about, the rates in terms of, until the end of the century, etc. But I want to try and use numbers in order to connect it to people's lives in a way that would give us some intuitive sense, that again, to connect it to something we're used to. What are we used to? For example, speeds are something we're used to. Well, like speeds, not in the 100-year time scale, but something more day to day. So let's try and find a way to do that. So you know what? I suggest, I think I have an interesting way to do that. I'm actually curious to see if maybe you'll come up with an interesting way as well. You might already have a good way. That's just a second. So I think it's actually also a good time to take like a 10-minute break. See if you come up with any idea. If you do, come and tell it either to me or to Lior or to Ron, and then we'll show you the way we thought about it as well. Okay? Good. See you soon. Okay, so just to be clear, this question is less well defined than like the previous question. Like it's not like how many babies come out into the world every day. It's a bit less, it's less clear what are we asking and how would we answer it. Okay? But still I want to try and approach it. And so what do you know about the speed of climate change?
It's increasing.
It's increasing. But if I need something about like what are we expecting? What? So a few degrees in a few years, right? Something along those lines. Okay, so there's this number, for example, of say, 2 degrees by, it depends, is it 2050, 2100, something along those lines, right? And actually, when talking about this is talking about the global average. I'm thinking about speed, I really thinking, on land. And I know if everybody's aware, climate change is happening more quickly on land than in the oceans because there's more inertia, thermal inertia and all sorts of other stuff. So it's going more slowly, meaning that if on average it's like 2 degrees, in the next 100 years, it would be, say, 3 degrees on land. We don't know the exact number, but it is something along those lines. Okay, so let's say I have 3 degrees in 100 years, 50 years. Okay, how do I turn this into a speed, into a rate?
It's already a rate now.
Yeah, so it's true. This is a rate in degrees per time. But I'm interested in the speed in a normal sense, meaning that I want to go from, degrees, this is degrees Celsius, right? I want to go from degrees Celsius, I want to go to a distance.
You want to go kilometers per hour?
Yeah, I want to do like kilometers per hour. Let's say climate change is walking.
Like energy? Like
So maybe you could do something like that.
So you need an radiative forcing, and that's
Rad-
the energy per meter squared. There's 3 watts per meter squared.
Okay, so maybe we could do something with radiative force. Okay, so actually it's nice. There's different ways to think about it. You see, again, it's an open-ended question. It's not like you don't have a textbook answer. But let me give you my way of thinking about it. So, we live on Earth, and we already have a temperature difference. There's the temperature here and there's the temperature there in terms of the poles versus the equator. So we have kind of like a gradient of temperature, a change in temperature over some distance. So this gives me a way to think about the relationship between temperatures and distance. Meaning if the temperature changes, it's the equivalent of us moving in space. Okay, if the temperature goes up 10 degrees, or let's say in Israel, let's say it went down, okay, it goes up by 10 degrees, it makes you feel like you're somewhere more south, more closer to the equator. Okay, and in that sense, the change in temperature is like a movement. Okay, now let's try and put numbers behind this. So what do we need to know? We need to know the delta T, the temperature, and we need to know the delta distance. So this is the equator, this is the pole. What's the change in temperature?
40?
Yeah, let's make it about, say, 40 degrees Celsius. More.
100.
I don't know. No, it's not 100. 10 to the whatever, yeah. Okay, what's the distance from the equator until the pole?
10,000 kilometers.
Yeah, so it turns out it's 10,000 kilometers, not just approximate, but actually it was somewhat defined at some point that way, which is something I learned in the course a while back. So it's about 10,000 kilometers.
What do you mean it was defined?
Yeah, so actually it turns out there's something like, I don't remember all the history behind, but when they decided about the definition of a kilometer, it was like 1 in a 10,000 of the distance between the equator and the pole.
So meters come from Earth, from the side of Earth?
I think in a way, yes, according to at least some measurement that they had, and then they changed it afterwards in the SI unit to some, a kilometer, like some meter they keep in France somewhere. But basically it comes, they defined it this way. Yeah, which blew my mind not long ago. Somebody was telling it from the students in the course. Okay, so there's something interesting here that happened, right? So I have 10,000 kilometers, 40 degrees Celsius. Okay, that's what I'm getting, right? Just, yeah.
Is it linear?
No. What can I do? Yeah, so I'm allowing myself the freedom to say, let's say it's a constant gradient. Of course, it's a bit more complicated. Good. Now, this is interesting. It's kilometers to degrees, which means that you remember I have this thing that I can multiply. I actually want to do a unit conversion in order to get to speed. So I want to do a unit conversion that would bring me to distance, and this would really allow me to do that, because now I can sort of like multiply by this characteristic gradient, average gradient of 10,000 kilometers being equivalent to, say, 40 degrees Celsius. And then what would I get? This divided by that would be 100 divided by 10. So I have and the units, degrees Celsius with degrees Celsius. So I have kilometers per year, and I have about 10 kilometers per year, which is about 1 kilometer per month, which is about what, 30 meters per hour? No, excuse me, per day, which is about 1 meter per hour. So according to this simplified model of giving a rate, by the end of the lecture, climate change would make it such, I don't know, where's north here? I think it's somewhere there. It would move the equivalent temperature, it would bring us 1 meter closer to the equator every hour. Yeah.
Why is this temperature gradient representative of like climate change gradient? I can alternatively choose the two sides in the equator where the gradient of temperature is 0, and then I would say that that climate change is a hoax because there's no change in temperature over distance.
Okay, so we have a change as a result of climate change, of increase in temperatures, and now I'm doing like an exercise or a way to represent it by saying this is equivalent, the change in temperature is equivalent to things moving for us, that the change in temperature is like moving in distance, moving in place. And the way to think about it, like a way to think about it is about it, we have this natural gradient on Earth of temperature between the equator and the pole, and therefore the change in temperature is equivalent to a change in time of movement. I think maybe if you think about it, you'll get it. In that sense, it's yeah.
No, I get the convention, just that it doesn't. What is like the intuition for choosing this specific gradient of moving on Earth from the equator to the pole?
Yeah, so I gave you the best intuition I have. Maybe I don't know. Maybe somebody else will have a better one, or maybe you'll have next time. That's the best intuition I have for now.
It's just informative and interesting, like to think of it in that way because it's relevant to us. We can contextualize our position on the Earth in relation to. I don't know if it might also be misleading because it seems that climate change is really slow if you look at a meter per hour. And you should probably give a direction. I think maybe a direction would help here.
Okay,
like
so I guess whether it's fast or slow, I think to me it seems actually pretty astounding that it's something that by the end of the hour it's going to shift in something that's not like a micron. It's like we're talking about some distance, but maybe you have a different perspective. That's also fine. I think you can connect it also. For example, let's say you think about adaptation of things to climate change. Okay, let's say you say, okay, climate change happens. But no problem, I'll just, if it was like a micron, no problem, I will just move, every 10 years we'll move like by a meter or whatever. But let's say, moving by 10 kilometers every year, that's more challenging. It depends who you are. If you're a tree, I don't know how you're going to move by 10 kilometers per year. You could disperse your seeds, etc., but it's also not trivial to disperse your seeds 10 kilometers per year. I think you got the idea. Okay, it's a way to, and you see, this is like, it's a different type of exercise. It's a way to try and connect between some phenomena and some scales that we're aware of, etc.
It's really like creating a metaphor. This is like a metaphor. It's not a real, right? It's like, so we can feel something about it.
Yeah, I don't know. It enables you to understand something in some way. I don't know if metaphor is the right metaphor for this, but okay. I think you could also connect it to say, if we were talking before about, the location of the COP, which is in one of the hottest, this year it's in one of the hottest countries in the world. It shows you that, if you multiply 10 kilometers per year, what's going to happen in the future. It wouldn't be the perfect location for, if you want to do a summer tour. The stadiums that were built there, I'm not sure you can do in that stadium a lot of stuff in the summer for many years. If you don't have great air conditioning, etc., which they do.
You could say that you have to get closer to the pole each year by 10 kilometers, and then it kind of it would freak the people out because in tens of years you would have no place on Earth with good temperature.
Yeah, so you can connect it in that way as well. Okay, good. or not so good, but it is what it is. We don't have good. Let's bring us back to the cellular level. You might remember we had this question that we're thinking about. What is faster? Transcription or translation? So in contrast to some of the things that we know kind of like intuitively or we carry in our head just because we've been living all our life on Earth and we've seen some things and we have great intuition for. These are the sort of things that are happening at the level of the cell in the microscopic level, so it's not so easy to have great intuition about them. But at the same time, I think you had, for example, the opportunity to look at this thing called key numbers, like a collection of a few numbers that are pretty useful in cell biology. So these sort of things could be guiding you and deriving all sorts of things. So let's see one such example. So if I want to approach this question, it's good usually to have some sort of schematic of what we're talking about. So let's say I have an mRNA, on top of which I have, no, I feel I want to start with the DNA probably, right? I have the DNA, I would have the polymerase sitting somewhere here. It would be running, let's say, in this direction and out of its, and I'll be having the mRNA coming towards here. And then I'll be having, on top of this, another machine. That's the ribosome. This is the polymerase. Which would be going in this direction. And out of that would come the thing that would create the protein. Good. And now I'm interested in the speeds. So what's the velocity of the polymerase? And I want to think about that versus the velocity that I have here of the ribosome. Anybody remember something about velocity of the polymerase, the transcription rate?
1,000 a minute.
1,000 a minute. 1,000 what?
Base per
Okay, so like 1 kilo base per minute. Any other values? Right, so I think, so let's see what we have here. We have 40 per second. And we also had 1 kilobase per minute, which is 1,000 bases per 60 seconds. So that's roughly about 20 per second.
It can be even faster for the PCR DNA polymerase. It's even half.
Yeah, so it could even be faster. Okay, so these are really kind of like the order of magnitude. Yeah, it could also do, I think 1 kilobase per minute is kind of like, it's also averaging over things that, it's engaged, less engaged. Maybe it's also in 30 degrees, not only 37 degrees. Anyway, so I think that's kind of like more of like representative of, say, 37 degrees. Okay. Rate of the ribosome?
2 amino acids per second. 20 amino acids. Yeah, 20.
Yeah, so the classic value that I think you also have is like 20 amino acids per second. Although I would say that it might be, let's say, in mammalian cells, different things, it might be slower. Okay, what does that mean about the original question?
60 base per second.
So I probably want to look from the amino acids and this is bases per second. So there's also a factor between this and this in terms of units, right? Right, that like if I'm doing 20 amino acids per second, it means that I'm reading 60 bases per second. right? It's like kind of like equivalent to.
But you're reading them 3 by 3.
Yeah, you're reading but still, when people gave the bases, this is bases, and it turned into amino acids. So it's okay. What does that mean?
It's happening faster.
Okay, so I hear two views. One is that translation. How was the question framed? Okay, so one is that faster, meaning translation is faster than transcription, right? And the other is that they're the same.
It's able to keep up at least. At least we know that there are some.
It makes sense that it's a little faster.
It makes sense. Why?
Both because there's more errors in translation than in transcription, and also there are some methods of stopping transcription that are based on the ribosome reaching.
Okay. More comments or thoughts? I'm looking for some. Everybody's participating already. Yeah.
I mean, it's also the polymerase is sort of the rate limiting step, right? If there's no new amino acids to read, we can't translate them into protein.
Okay, so I'll say the following. First of all, for me, given the kind of accuracy we're talking about, I would call this the same. Okay, 60 versus 40, that's kind of like the same for me in the level of accuracy we talk about, because all of this depends on the temperature, it depends on the organism, it depends on which exactly sequence is it read, and lots of stuff, what the cell ate for breakfast, lots of stuff could matter, and in that respect, it's kind of like the same. There's also, by the way, a more deeper thing that I think was pointed out here. The ribosome can't, let's say in bacteria. In bacteria, there's this what is it called? Co-something. There's like the translation works with transcription concurrently. Okay, which means that there's no way that the ribosome could go faster than the polymerase, just because it requires the polymerase to give it substrate in order to go forward. Okay, so there's kind of like even a speed limit, such that when they're, at least in bacteria, you can't have the translation happening faster. Although in other organisms where it's separated, who knows, everything could happen. Okay, but it's roughly the same. Okay, now, even so, what you can't know from this is that it's on the order of, say, a few tens per second. It's not a few hundreds per second. It's not a few thousands per second. It's not, point something per second. And you'll find that this is useful if you know that. Because then you can do all sorts of sanity checks on claims and phenomena and things like that. And it's useful. I hope you'll find that also useful in the exercise that you have in the coming exercise on rates. By the way, there's a deeper question, and that is, why is it so? What is the origin? Why isn't it much, much faster, for example? And it's which one? Either. Like, it seems like I would have been, maybe, I would have been much smarter if instead of being able to make proteins at this rate and transcription at this rate, if I could do it 100-fold faster, maybe we'll just be, much better in all of our capabilities as humans. Evolution, why doesn't evolution push us? It seems more efficient to do things faster, kind of like, computers becoming better and then you're able to do more stuff. And just to show, it's not completely impossible in a way, maybe, because if you look, what's very similar to this process of transcription?
Replication. DNA replication.
Yeah, DNA replication, right? That happens also with the polymerase. Just instead of RNA polymerase, it's DNA polymerase. Anybody know something about the rate of the DNA polymerase?
Similar.
It's about faster, slower. It's actually much faster. It's about 1,000 bases per second. Okay, way faster. Which makes you wonder, if you could do much faster, why is it not also for the RNA?
Cost benefit, no? You have a
What?
lot in DNA polymerase, you have a lot more to do. You have a lot more to copy, and so if you're taking your time with it, it might not be beneficial, from a fitness perspective.
Yeah, from an energetic point of view, the polymerase is lazy. It wouldn't create, more RNA copies if it doesn't have available ribosomes to, do something with it.
So I would say, I think it's an interesting question. Okay, and I would say that there's no perfect answer that I'm aware of. There is, by the way, interesting answers, I think, about the rate of the ribosome. If anybody wants, we could talk about why can't it be much faster. On the transcription, I don't have a great answer, which I think is also an interesting feature for me. It shows how, again, being quantitative about stuff brings up new questions that could give you food for thought or scientific thought, etc. Okay, I want to rush for quick comment.
Just maybe it enables better regulation.
Yeah, okay, so there's all sorts of hypotheses, that's great, and that's fine. Yeah?
Are we ignoring the fact that we have more than one copy of the ribosome and the RNA polymerase, and then from one mRNA we have more than one protein?
Yeah, so we're not ignoring it. That's also part of the thing, and then you could still hope that, like, if you did things much faster, it would have been better in some ways about that question. About the original question, I'm talking about here just, per polymerase, per ribosome. It's true that now you can have several ribosomes sitting on the same mRNA and all sorts of stuff. That's true, but unrelated to the question of what is the speed of each one separately. Nice. So I think we did this. Okay, the final thing that I want to touch on is also relating to rates, but now I want to talk about what's the other important process inside cells in terms of speeds and rates?
Diffusion.
Diffusion, exactly. So let's talk about diffusion and its rate. So how fast is diffusion?
Depends on what?
Okay. How long does it take a protein to move across a cell by diffusion? Okay. A. Now I'm interested both in, say, bacteria and mammalian mammal cell. So let's give a few options. Let's say this is 10 milliseconds and this is 100 milliseconds. Let's say it's 10 milliseconds and 1 minute. I didn't put microseconds at all. Okay, let's make it 10 microseconds and 100 microseconds.
Why would it be faster in mammalian cell?
No,
slow.
Let's make it 1 second, 10 seconds, etc., etc. Okay, I'll just. Anybody has an intuition? Who's voting for A? Who's voting for B?
By diffusion?
Who's voting? Yeah, by diffusion. Voting for C? Who's voting for D? Okay, so I could tell that, like, there's a statistically significant tendency in the question about diffusion to raise your hand much lower than the previous one, like this. It's like something like this, which I think reflects something. I think it's no coincidence. I think, like, it's clear to us that we don't have that great of an intuition about this stuff, right? Okay, so how do we still try to make progress with this? So I have a cell. This is bacterial or mammalian? I think it came a bit mammalian. Yeah, so let's do it bacterial. That's first. Okay, and now I have a protein here. And it does diffusion. And we want to know, okay, it doesn't have to go to the other side. Maybe it doesn't want to go to the other side, but it just, it just diffuses, and we want the average time until it makes, a distance of 1 micron. Okay, which is how I'm thinking about the bacterial cell. Okay, so the question is, first of all, you need to have some law which tells you something about the relationship between the distance that you'll cover and some other stuff. So what would dictate the rate at which things would move in bacteria, or by diffusion, sorry.
Density.
Temperature.
Okay, so let's write that down. So we have the density, we have the temperature, the size of the protein,
Concentration gradient.
concentration gradient,
The size?
Yeah, sorry.
The protein?
okay, so there's all sorts of stuff. And there's an elegant way to get out of all this mess. And that is to just think about the distance that you're covering as a function of the time that elapses. And all of the rest of the stuff, to just call it D. Okay, so you just bundle it up, all the dependencies on temperature and density and the size. Concentration gradient is something else. Let's not talk about it now. If you want, it's a bit non-intuitive. So there's also, by the way, for some historical reason, it's different if you do it in 1 dimensions or in 2 dimensions or in 3 dimensions. And because of that, there's also a factor of 6. Some odd fact. Well, yeah, forget about it. Okay. But now the question is whether this is equal to that or there's something else happening here. If it was just like that, life would have been simple thinking about diffusion, because that would mean that as time elapses, you're making more and more distance, right? In a what's known as proportional manner. But diffusion is kind of different, right? How does diffusion work? It's kind of like this thing that like you go and then you go back. Let's say if it's 1 dimensional, then you go back and then you go, and you throw like a coin, and that's how you decide. And as you can imagine, when you do this, you don't get as far as if you're going proportionally, like in a constant velocity. And now you can do math around it, and you find out that really as a result, instead of this being equal to this, it's equal to the square root of this. Not a big deal, just a square root. Okay, so this is the equation for what's the distance as a function of time. And now let's see what are the implications of that.
The square root is for all dimensions? Or?
Yeah, it's crazy, independent of dimension. So it's really also super interesting that this whole thing of like whether you're in 1 dimension, 2 dimensions, 3 dimensions, n dimensions, it's always square root. The only thing that changes is this 6. And then it's also a question, how do you calculate D when you're in 1 dimension? It has a bit of a different meaning because density is a bit different and all sorts of things like that. Good. So I can start doing some work. Let's say if I have this, I can also, I know the distance already, right? I know the distance I want to go, R or L or whatever. And what I'm curious about is the temperature, is T, the time, right? So I can just take this, I can do T equals, and I just square this, it will be R squared divided by 6D. If I want to start and do some calculations, I'm still missing something, right? D. What is the value of D? What do you think? 10. Yeah, let's do 10. Yeah, so what are the units, right? That's super important.
Yeah.
Yeah, so it's 10, and I think it's the micrometer square per second, right? Let's see if that, I think that's the units. Let's see if it makes sense. I don't remember anything almost by heart. This is units of micrometer squared. So if this is micrometers squared per second, micrometer squared, go. The 1 second you see would go up, it would be T. That's good, I remember it correctly. Okay? By the way, don't tell anybody, but I remember I was sitting in this room when I was a PhD student, and it was, anyway, too embarrassing. But I did like a stupid mistake. Anyway, Naama Barkai was giving a lecture, and she was asking something about diffusion, and I gave a value, and it was off by several orders of magnitude. And my mentor at the time, Uri Alon, was sitting next to me, and I could tell that he was like, he said something, no, sorry. Immediately he was like ashamed by what I said, and it all happened in this room. Like Siri and I was sitting probably where you're sitting, so I still remember it. So I guess the lesson is that you can make mistakes and still continue in life, and it will be okay.
Lifelong trauma.
Yeah, but it would come back to haunt you. Okay. It's funny, I like the story like really hit me now. Okay, so we have the diffusion, we have D. Let's start play around, do some work. So let's see, I want to do the T for bacteria. So R squared would be what?
1.
Yeah, it's very nice. 1 micrometer squared divided by, I have the 6 times 10 micrometer squared per second. What is this? It's 1 over 60 of a second, or roughly 10 milliseconds. You're with me?
But we just needed to know this somehow, right?
Yeah. So okay. So here's the thing. Like it's not like you need to know what
D.
Yeah, you need to know D. Exactly. So again, I don't want to give you a sense of, there are some things that I can do, just out of pure logic in a way, or like things from our complete intuition, things that we know, like what's the weight of a person, or what's the turnover of something. There are some other things like the size of the Earth, or the diffusion constant, or the rate of transcription, that you do need to know something. But I guess what I want to tell you is that you don't need for every question to know everything, over. If you carry a few numbers in your head that you know because you heard at some course or it's useful, you can infer way more things. Like you don't need to remember the time it takes for a protein to pass from one point to another by diffusion. You just need to know what is a diffusion coefficient or diffusion constant. If you know that, you can infer lots of stuff. Okay, and I'm telling you there's a range of not like an infinite number of numbers that with which you can reach like a crazy combinatorial space of solutions to many questions you'll find in life. Okay, so we got the 10 milliseconds. Let's do the similar thing for bacteria, for this mammalian cells, what is the relevant time scale, length scale? That would be, say, 10 micrometers. So now we could do this again. The time for the mammalian cell. What do we have here now? R squared. We have 10 micrometers squared. So this is like now 100 divided by 60. And we're getting about 1 second. Okay. So now my challenge to you is when we're talking about this mammalian cell, this was just like, I don't know, like some standard thing you often use in tissue culture. But there's all sorts of other types of mammalian cells. What's an interesting one that I might be interested in now?
Neurons. Because they're very long.
So let's talk about neuronal cells. Okay, let's think about neurons. And you need to reach across an axon, right? You have the nucleus somewhere. I never remember, so neuron cell, something which looks like this. And you have the nucleus somewhere, and you're producing, and let's say you have a protein, and you want it to reach from one side to the other. What would be the size of the axon?
1 meter?
It's the longest.
Yes.
Yeah, so it could be 1 meter for the longest. But let's say, let's not go that far. Let's just go for something, that you probably have already in your brain. Let's say this is 1 centimeter. Okay? How long does it take a protein to reach across 1 centimeter axon by diffusion.
It's not really three-dimensional.
What?
It's not really three-dimensional.
Yeah, it's not really 3-dimension. So because it's not 3-dimension, instead of 6, you can use a 4.
And diffusion is
Okay.
not the
So the question is, how long would it take? And I'm not joking. That's what it comes out to, which is interesting. We could talk about the intuition, but that's for a different time. Okay. So the question: would it take 1 minute, 1 hour, 1 day, 10 days? Who's voting for 1 minute? A few. Who's voting for 1 hour? A few. Who's voting for 1 day? A few. Who's voting for 10 days? Okay, nobody wants. Okay, so we have 4 people for each answer, and half of the people are abstained. Okay, but I would challenge you to take 3 minutes, which is somewhere between here and here, to try and derive it yourself. What? With your neurons, yeah. Use your neurons to answer this question. Well, I remind you, I just omitted it, we had t equals r squared divided by 6 times d. Four. Actually, no, it's still 3-dimensional. For the protein, it's easy to, it's somewhere between 4 and 6, whatever. Anybody wants to change the vote? So let's do it together. So we were working with these units of micrometers, right? And now we have a 1 centimeter long axon. So we need to go from this to that. Right, so 1 centimeter, that's equal to 10 millimeters. Every millimeter is how many microns? Yeah, so it's 1,000. And therefore I have about 10 to the 4 micrometer. Good, I see some people smiling. They're already happy about, the result that's going to come out. Good. So r squared, I need to plug in 10 to the 4 micrometers squared, divided by, again, 6. Let's make it 4 times 10 micrometers squared per second. By the way, I'm keeping the 6 because actually even though to us it looks 1-dimensional, for the protein, so this has a width. How much? A few microns, probably a few microns, not a micron, few microns. When you are a few microns and you're a protein, the world looks, infinite to you. You don't see any of the barriers. So you're just doing your random walk. It's true that when you reach the end, you hit and you go back, but it doesn't care so much about it. Okay, so it's really effectively, it looks like 3-dimensional to it. Or there's a cool trick they do in math, they look at diffusion at every different axis. So on this axis, it's anyway, it's complicated. Okay, so back to here. 10 to the 4 squared, so we have 10 to the 8 divided by 10 to the 2. Micrometer 2 seconds. So we have 10 to the 6 seconds. What can we do with 10 to the 6 seconds? So I remember, you remember how many seconds there are in a year?
Pi multiply.
Yeah, pi 10 to the 7. That's how I like to think about it. It's very close to pi 10 to the 7. So like 3 10 to the 7. So that's 1 in 30 out of this. If I have 300 days in a year, divided by 30, it's 10 days. Of course, you can do it. You don't have to do it in this trick that I just did. You can just think about a million. Then you say, okay, 60 seconds in a minute times 60 minutes in an hour. So that's 3,000. So I need to divide by 3,000. It's like 300 hours. 300 hours. That's about 10 days. Or you can do it step by step. I'm just bragging here. Okay, so 10 days. What do you think?
It can be right or more.
Well, could it be right?
Yes.
No. No.
Yes, but you use ATP to move.
That's we have to. Why not?
You don't move it at all in neurons. You only move electricity.
Yeah.
No, but still the cell need to be
Just a second. So you're saying in the neuron
You don't need to move chemicals in the axon. You only move electricity, and then you move the chemicals from the end to the dendrite of the.
Okay, so let's take it slow for a second. So you're giving a good point. The main function of the neuron is to pass an electric signal, and the electric signal is not what we dealt with. That's a different lecture to try to. Okay. At the same time, one could ask, in order to run these electric signals, you need to have some transporter here, right? You need to have on the membrane. There's also these things, channels that open and close, and all sorts of stuff like that. Where did the channel come from? Or like it needs to, every time it needs to replace itself. Or there's all sorts of proteins here, right? I know there's sitting here in the top, in the synapse, there's all sorts of proteins. That's my friends in neuroscience telling me. These proteins have to come from somewhere. Where are they coming from?
The nuclei.
They're coming from the nuclei. So at some point, things have to move from here to here.
But they don't have to move by diffusion. They can move by other means.
Okay, but just
Also,
before
they come
that,
back from the synapses.
what?
They can stay there for 10 days. They come back from the synapses all the time. Like they go out and they come back.
Yeah, okay, yeah, but at least once they have to. At least once they have to come. Or at least I think they continue to come.
And turnover can be really slow.
Yeah.
Yeah.
It could be slow. Yeah. There's also another thing that you could say. Hey, maybe I don't need to move the protein. I could have, for example, the ribosome sitting here, and just the ribosome making it like in situ, like where it's needed.
mRNA, which is bigger.
Nice. So yeah, so then you need to move the mRNA, and in contrast, when you need to move the mRNA, that's also another good point. You'll need to move less mRNAs, because from every mRNA you can make a lot of proteins, but you still need to move the mRNA that now you know is not a piece of cake, right? It's a heavy cake.
The worst problem is that if you need 10 days to move the protein or the mRNA, it will degrade before it gets there.
That could be another problem, that there's a problem of degradation. Okay, so what's the solution?
Active movement.
Right, so it doesn't move by diffusion. And there's these very cool movies, if you want to look at them on YouTube, of how, there's these things sitting on these roads, and they're like, myosin, not myosin.
Monoprotein.
Yeah, kinesin and dynein, etc. And they're like grabbing on whatever things they have on their head, like carrying as if they're carrying a bag, and they're taking the proteins with them, and they're walking, and people, spend years on whether they're walking this way or whether they're walking this way, also things like that. But there's a really beautiful, beautiful understanding of how mechanistically that happens, that they're able to move at the rate of, so they're moving at the rate of about 1 micrometer per second. That's the rate of molecular motors, the velocity. Is that fast?
Still quite a lot of time. No.
Yeah, so
but it's linear movement, it's not diffusion.
No, but
You just go one way.
Yeah, but 1
It's
centimeter.
It's
linear with the distance.
It's less than the diffusion we calculated for the material.
Right, so there's something interesting here, right? As you point out, we talked about it before for the bacteria, and there it took us just 10 milliseconds to cover a micron. So it was much faster by diffusion. So now I'm replacing this by something that goes almost like 100 times, or whatever it was, like 100 times slower, and still I'm happier, or my brain is happier.
Because of the size of the cell? That's the reason?
So why?
The small cell diffusion would be more efficient.
Because diffusion is non-linear movement, and this shuttle is, you just go one way, and that's it. Diffusion goes back.
Yeah.
It's like I would be much happier taking a bus or a train that goes on the road somewhere than just hopping on a very, 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 very high speed vehicle that goes everywhere else. I mean, I really, it has an origin and a destination, the protein. It's needed somewhere. So the linear movement is much more efficient.
Okay, more ways to, yeah?
This process is diffusion limited as well. So it can't be faster than diffusion in terms of the amount of, like, it's an active process, so ATP has to diffuse there. And so it makes sense that you can't do it quicker.
Okay, maybe. I think the key issue, which I think we brought to an interest, is this thing about, it's all sitting in the square root that we had before, which is all about like whether you're really directional or not. So diffusion at the microscopic scale is very, very fast, super fast. And therefore it could push you this 1 micron in milliseconds. And that solves many problems, like, it really enables the miracle of life to work. But when you need to go over longer distances, it slows down because of this square root. It doesn't sound like a big deal, but it turns out it is a big deal. That when the distance goes beyond, when it was 1 micron, okay, 10 microns, we already moved to a minute. When you want to move way more, 10 times more, 100 times more, it's all squared. And then it becomes so slow that it's just like, wouldn't solve the problem. And then even if you're slow, but you're just directionally continuing, such that you're proportional with time, it becomes better. So you're 100 times worse in terms of rate for the short distance, but for the long distance, you are way, way faster. Okay, how much faster? Let's see. 1 micron per second, it means it will take you 1,000 seconds to make 1 millimeter, or 10,000 seconds. So 10,000 seconds in comparison to 1,000,000 seconds. Okay, so you start at 100 times more slowly, and you're going to finish 100 times earlier. How cool is that? I didn't even plan it. It's like really came out really elegant in terms of the numbers. Okay, you're starting 100 times more slowly for the 1 micron, and you're finishing 100 times faster in terms of reaching a centimeter.
Slow and steady.
Slow and steady. Okay, I think it's a good point to wish you a slow and steady week. Try to keep, moving forward at a good pace and get far.